Yeah, so this is a little typical kind of example. Whomsoever wanted to write a detailed answer for IES kind of examination, where the function is given as g of s is equal to k by s into n plus 1 into s plus 2. So now when we have discussed this one already, where we wanted to take a first of all Nyquist contour. From the Nyquist contour we wanted to draw the Nyquist plot. So the Nyquist contour is drawn by just keeping s is equal to j omega, and then we are trying to draw a infinite semicircle limit r tends to infinity and that particular function, that one we are calling as s2, and s3 we are calling as the inverse image of the s1, and then we are calling one more semicircle where r is tending to 0 and limit r tends to 0, and then so on. Now, first of all, as you know, we have to draw the S1. S1 is something like a polar plot where omega is starting from omega is equal to 0 to omega is equal to infinity. So first of all, we had to find out the magnitude and the phase plot of magnitude and the phase of the given transfer function. That is equal to k by omega into omega square plus 1 into omega square plus 4, and the phase is since denominator is yes is there, that one if it is going to numerator, minus 90 minus tan inverse of omega minus tan inverse of omega by 2. So substituting the value of omega is equal to 0, so k by 0 something is infinity, so and minus 90 and remaining are 0, so this is minus 90, and when omega is equal to infinity, 1 by infinity is 0, minus 90 tan inverse of infinity is 90, minus 90 minus 90 minus 270. Now we have to draw the plot that is starting at infinity of minus 90 degrees, and it is going to in 0 at minus 270. So that is how this plot is drawn. That is S1 we are calling. Now the same S3 is the inverse image of S1. Okay, so whatever the image is there, whenever it is starting from minus 90 to minus 270, inverse we are drawing. Now we are trying to close that path because the Nyquist contour is also closed. The Nyquist plot also should be closed. Now S1 we have drawn, S3 we have drawn, and the path that is closing between S2, S3 to S1, that is also getting closed from S3. It is starting from S3 and it is flowing to S1 because it is traveling from plus pi by 2 minus pi by 2. So that one we have to draw here. Now the important thing is the one which is what will happen when S4. How are you going to draw the S4? The S4 you know already. S4 we have drawn as, so initially what we did, we took a transfer function g of s is equal to k by s into s plus 1 into s plus 2, that anyway we are taking into the same function that we are taking. After doing that, we are applying the limit, that is r tends to 0, where s is equal to r into e to power of j theta. So since when the s is almost tending to 0, I can discard the value of s because 1 and 2 are little more higher. So limit r is tending to 0, so it is 1 by 2 is 0.5, 0.5 k divided by s is equal to r into e to power of j theta. Now, when I am taking it to numerator, since r is tending to 0, this will become 1 by 0 is infinity. Infinity into the e to power of theta I am taking to numerator, it will be e to power of minus j theta, where theta is traveling from minus pi by 2 to plus pi by 2. Why I have taken this, whether it is going in the same direction or not, I wanted to see. So, when I am substituting the value of pi by 2, so this is infinity, it is e to power of j pi by 2. So, to infinity e to power of minus pi by 2. So it is traveling easily from plus pi by 2 to minus pi by 2. So we are sure that how it is traveling. Now let's find the value of k when the system is stable and when the system is unstable. So let us easily do that by putting the value of s is equal to j omega. So let's find that k by, okay, for what values of k the system is stable, we need to find that. Okay, k by j omega into j omega plus 1 into j omega plus 2. Okay, for our given transfer function I want to write this k by j omega into j omega plus 1 into j omega plus 2. So now I will multiply all the transfer function, that I will get k by j omega into, so j omega into j omega minus 1 into omega square plus 2 j omega plus j omega plus 2. Now again what I will do, I will take out the part of j omega and non j omega separately. After that I will make sure that, because the system is stable, we have to find out where actually the value is getting crossed, right? So when it is crossing the negative real axis, the imaginary part, we wanted to make it 0. That is the reason why I wanted to take the imaginary part and the real part separately. Okay, so from calculations what I get is k by minus 3 omega square plus j into 2 omega minus omega square. So I wanted to make that 2 omega minus omega square. Okay, I wanted to make this 2 omega minus omega square that to be equal to 0. When I make equal to 0, the imaginary part is equal to 0 and the real part, right? So omega is equal to omega PC, that is phase crossover frequency, is equal to root 2. So substituting value of root 2 in the k by minus 3 into root 2 whole square, wherever the real part we have left, right? So that's what I'm substituting. I'll get k is equal to that is equal to minus k by 6. Okay, minus k by 6 I'm getting. So that minus k by 6 I have to equate it to minus 1, because my area of interest is how many times it is encircled the minus 1, right? So k is equal to 6. So my margin, that phase margin value is 6. Now we have to check whether what will happen when the k value is greater than 6 or less than 6. So we'll write the two cases. In the case 1 where k margin is greater than 6, and case 2 where k margin is less than 6. Now by substituting the value of k is greater than 6, what will happen? First of all, let us take the k value of k less than 6. Here the number of poles, the number of encirclement is equal to p minus z. So p is 0 and n is 0. So the number of zeros on the right hand side is also 0. So for every value of k is less than 6, the system is set to stable. But for k greater than 6, if you see the figure, you will get minus 2 encirclements. Okay, so minus 2 is equal to 0 minus z, z is equal to 2. So you have to cross check the figure. So then you can see that the system is unstable completely here, because the number of encirclement on the 0 side is 2.